Alright guys, this is the last little bit that I usually lump in with intermolecular forces, and we're going to talk about the structure of solids. So solids, as we know, all have the same properties. They're hard, they hold their shape, they have a definite volume to them, so they can't like expand to fill a container like a gas does, that kind of stuff. They have the least amount of kinetic energy and the most amount of attractions between each other. They have very slow reactions. Because their molecules aren't moving as fast, things like that. These are all properties of solids that we've already studied and know about. But what you don't know is that there's different structures that the molecules inside of a solid can take. So you can have either a crystalline structure or amorphous. So if we're talking a crystalline structure, the atoms or ions or molecules form a very well-ordered and defined arrangement that'll maximize the attractive forces between the particles. So if you think about like salt or sugar, these are crystalline, and you can actually, when we look at them under a microscope or under a magnifying glass, or even if you just have really good eyesight, you could go to a well-lit area and you could see it yourself. You can see that there's a very specific pattern in the way that the crystals of sugar or salt look. Amorphous is when the particles have no specific shape or order to them. So we've got a bunch of different types of solid: molecular, a covalent network, ionic, and metallic. Well, that's what we're going to go over now. So for molecular solids, the tiniest bit of, or tiniest unit of matter is going to be the atoms or molecules. They will have London dispersion, dipole-dipole, and hydrogen bonds being exhibited throughout them, again depending on its polarity. So if it's non-polar, then the only thing it'll have is the London dispersion, but if it's polar, it'll have dipole-dipole or hydrogen bonds as well. But molecular solids tend to be pretty soft. They have an intermediate melting point, so not too high, not too low, and they're pretty poor conductors, and that's going to be for a very specific reason that we will talk about when we talk about metallic bonds. This is an example of a molecular one. You can see that while the atoms or the molecules are arranged in a pretty specific way, they're not very tightly arranged. A covalent network is a connection in a network of covalent bonds. So now we're talking about things that are not polar, because covalent bonds are all on the same side of the periodic table. They're all nonmetals, so they don't have a big enough difference in its electronegativity to form a polar bond. So we're talking about covalent bonds and London dispersion being the main things holding these particles together. They do tend to be very hard with very high melting points, but still very poor conductors of electricity. These are some examples. So a diamond is one of the most famous examples, right? Because they're one of the hardest substances that we know about. They're obviously very crystalline. That's what gives them that pretty reflective surface. They are made up of pure carbon. So what's interesting between a diamond and graphite, for example, is again, it's pure carbon, but the way that they're arranged. So a diamond has a much more structured arrangement than the graphite, which is like what you find in your pencil lead, even though they have the same carbon in them. So it's not different. Silica is another example of a covalent network that forms a lot of our minerals and stuff. So when you go outside and look at rocks and they're shiny or they have crystal structures in them, that's usually the silica. Ionic is another type of solid. They have positive and negative ions that are the basic units to form up these ionic solids. They have electrostatic attraction, so remember that's the positive and negative, the attraction between a positive and a negative. But they also exhibit London dispersion, dipole-dipole, and ion dipole because they are ionic. So because they can form polar bonds, then they can exhibit all of those. They are very hard, but they also are pretty brittle, which means that they can break easily. They have a high melting point, but are still poor conductors of electricity. These are all examples here. So really any type of solid that's got a positive and a negative to it. So sodium chloride is one of our big examples. It's like basically table salt, but you can have all these other examples as well. Metallic solids are base forms of atoms. They will have metallic bonds and London dispersion forces between them. And they have a range of hardness, so they can be very soft to very hard. They can have very low melting points to high melting points, but almost all of them are good conductors of electricity because of the way that their electrons are formed, because of the way that those electrons can do what we call delocalization. So in this picture up here, you've got a positive, which is representing our nucleus, and then this red dot, which represents the electron. So at any point in time in a metallic bond, this electron does not have to stay with this one atom. It can delocalize or move away from that atom and be shared basically between all of them. So instead of this red staying with this nucleus or this red staying with this nucleus, it can become more like this, where the electrons can move freely between all of them. And because electrons are then able to move freely, that means that they can conduct electricity, because electricity, as we know, is that movement of electrons.